Welcome back to our journey through the TCP/IP model. We're in the third unit or third chapter, which is a study of the transport layer. This is the layer that's responsible for end-to-end communication. That is to say, responsible for ensuring that the data sent is the data that is actually received by the application. We're beginning lesson 12 of our second in a series on the transport control protocol of the transport layer. So let's pick up where we left off. Two of the most important fields in the TCP segment header are the sequence number field and the acknowledgement number field. These fields are a critical part of TCP's reliable data transfer service. TCP views data as an unstructured but ordered stream of bytes. Now what that essentially means is that the application has sent a message to the transport layer to be transmitted across the network. And what the transport layer sees is a string of bits. It has no idea of any shape, form, or anything else of that string of bits. It just sees a string of bits. Thus the unstructured part of that statement. But it does acknowledge, or it does recognize, that those bits have a specific order. If you know anything about ASCII code using the binary system, you know that if you rearrange those bits, they take it on an entirely different meaning. Let's continue. TCP's view of sequence numbers reflects this view in that sequence numbers are over a stream of transmitted bytes and not over the series of transmitted segments. The sequence number for a segment is therefore the byte stream number of the first byte in the segment. Let's look at an example. Suppose that a process in host A wants to send a stream of data to a process in host B over a TCP connection. The TCP in host A will implicitly number each byte in the data stream. Suppose that the data stream consists of a file consisting of 500,000 bytes, that the maximum segment size is 1,000 bytes, and that the first byte of the data stream is numbered 0. TCP then constructs 500 segments out of that data stream. The first segment gets assigned a sequence number of 0. The second segment gets assigned a sequence number 1000. The third segment gets assigned a sequence number 2000, and so on. Each sequence number is inserted in the sequence number field in the header of the appropriate TCP segment. Now let's consider acknowledgement numbers. Now bear in mind we are talking about TCP, Transport Control Protocol. We are not talking about one of the reliable data transport protocols that we just finished with the 0 and 1 acknowledgements. Recall that TCP is full duplex, so that host A may be receiving data from host B while it sends data to host B as part of the same TCP connection. Each of the segments that arrive from host B has a sequence number for the data flowing from B to A. The acknowledgement number that host A puts in its segments is the sequence number of the next byte host A is expecting from host B. Suppose that host A has received one segment from host B containing bytes 0 through 535, and another segment containing bytes 900 through 1000. For some reason, host A has not received bytes 536 through 899. In this example, host A is still waiting for byte 536 in order to recreate B's data stream. So A's next segment to B will contain 536 in the acknowledgement number field. Because TCP only acknowledges bytes up to the first missing byte in the stream, TCP is said to provide cumulative acknowledgments. In this example, host A received the third segment, bytes 900 through 1000, before receiving the second segment, which contained 536 through 899. Therefore, the third segment has arrived out of order. The question is, what does a host do when it receives out-of-order segments in a transport control protocol connection? Interestingly, the TCP does not impose any rules here and leaves that decision up to the people programming the TCP implementation. Further, there are basically two choices. Either the receiver immediately discards out-of-order segments, or the receiver keeps the out-of-order bytes and waits for the missing bytes to fill in the gaps. Clearly, the last choice is more efficient in terms of network bandwidth and is the approach taken in practice. The initial sequence number, by the way, is not necessarily 0. Both sides of a TCP connection randomly choose an initial sequence number. This is done to minimize the possibility that a segment that is still present in the network from an earlier, already terminated connection between the two hosts is mistaken for a valid segment in a later connection between these same two hosts. TCP, like that reliable data transport protocol, uses a timeout retransmit mechanism to recover from lost segments. Although this is conceptually simple, many subtle issues arise when we implement a timeout retransmit mechanism in an actual protocol such as transport control protocol. How much time is allocated for the interval? Clearly, the timeout should be larger than the connection's round trip time, that is, the time when a segment is sent until it is acknowledged. Otherwise, unnecessarily retransmissions would be sent. But how much larger? How should the round trip time be estimated in the first place? Should a timer be associated with each and every unacknowledged segment? Let's begin our discussion of TCP timer management by considering how TCP estimates the round trip time between the sender and receiver. This is accomplished as follows. The sample round trip time for a segment is the amount of time between when the segment is sent, that is, passed to the internet layer, or to the network layer, and when an acknowledgement for the segment is received. Instead of measuring a round trip time for every transmitted segment, most TCP implementations take only one sample round trip time measurement at a time. That is, at any point in time, the sample round trip time is being estimated for only one of the transmitted but currently unacknowledged segments. Also, TCP never computes a sample round trip time for a segment that has been retransmitted. It only measures round trip times for segments that have been initially transmitted. Obviously, sample round trip time values will fluctuate from segment to segment due to congestion in the routers and to the varying load on the end system. Because of this fluctuation, any sample round trip time value may be atypical. In order to estimate a typical round trip time, it's therefore natural to take some average of round trip times. TCP maintains an average called estimated RTT of the sample round trip time values. Upon obtaining a new sample round trip time, TCP updates the estimated RTT according to the formula you see in this slide. The formula is written in the form of a programming language statement, and the new value of estimated RTT is a weighted combination of the previous value of estimated RTT and the new value of the sample RTT. TCP provides reliable data transfer by using positive acknowledgments and timers in much the same way UDP does. TCP acknowledges data that has been received correctly, and then it retransmits segments when segments or their corresponding acknowledgments are thought to be lost or corrupted. Certain versions of TCP also have an implicit negative acknowledgement mechanism with TCP's fast retransmit mechanism. Certain versions of TCP also have an implicit negative acknowledgement mechanism. With TCP's fast retransmit mechanism, the receipt of 3 duplicate acknowledgement for a given segment serves as an implicit negative acknowledgement for the following segment, triggering retransmission of that segment before timeout. Remember, the acknowledgement sequence number was the next sequence number expected. TCP uses sequences of numbers to allow the receiver to identify lost or duplicate segments. Just as in the case of our reliable data transfer protocol, TCP cannot itself tell for certain if a segment or its acknowledgement is lost, corrupted, or just delayed. At the sender, TCP's response will be the same. Retransmit the segment in question. TCP also uses pipelining, allowing the sender to have multiple transmitted but yet to be acknowledged segments outstanding at any given time. We saw earlier that pipelining can greatly improve a session's throughput when the ratio of the segment size to the round trip delay is small. The specific number of outstanding, unacknowledged segments that a sender can have is determined by TCP's flow control and congestion control mechanisms. TCP flow control and TCP congestion control will be discussed shortly. For the time being, we must simply be aware that the TCP sender uses pipelining. Let's close our study of TCP's error recovery mechanism by considering the following. Is TCP a go back in or a selective repeat protocol? Recall that TCP acknowledgments are cumulative and correctly received, but out of order segments are not individually acknowledged by the receiver. Subsequently, TCP need only maintain the smallest sequence number for a transmitted but unacknowledged byte and the sequence number of the next byte to be sent. In this case, TCP looks a lot like the go back in style protocol. But there's some striking differences between TCP and go back in. Many TCP implementations will buffer correctly received but out of order segments. A proposed modification to TCP, the so-called selective acknowledgement, allows a TCP receiver to acknowledge out-of-order segments selectively rather than just cumulatively acknowledging the last correctly received in-order segment. When combined with selective retransmission, skipping the retransmission of segments that have already been selectively acknowledged by the receiver, TCP looks a lot like a selective repeat protocol. Therefore, TCP's error recovery mechanism is probably best categorized as a hybrid of go back in and selective repeat protocols. I think that's enough for this section, so let's take a break. Study your notes. Make sure you update your study guide. Take care of any assignments that you may have, and when you're ready, come on back for lesson 13.